A used propane tank costs about $150. The lithium battery your installer quoted costs $10,000 or more, and it comes with a written promise that it will fade. One of those two things does not degrade at all. By the end, you will know exactly what that tank can power, and why you cannot buy one at any hardware store in America. The tank is a pressure vessel, and that word is doing real work. A propane tank built to the American Society of Mechanical Engineers standard is engineered to hold a liquefied gas under sustained pressure, sitting outdoors, through summer heat and winter cold, for decades, without anybody checking on it. The steel is thicker than the portable cylinders you swap at the hardware store. The welds are different, and the certification works differently too. A portable DOT cylinder, the kind under your grill, has to be requalified every 12 years to stay legal. An ASME tank is certified once, at the factory, and that certification holds for the life of the vessel. Here is the number that matters for what comes next. These tanks are engineered to contain liquefied propane at around 250 pounds per square inch, in direct sunlight, on the hottest day of the year, with a safety margin built on top of that. Which means if you fill one with ordinary compressed air at 150 pounds per square inch, you are operating well inside a design envelope that was drawn for something far more demanding than air. And the storage arithmetic that comes out of that is not close. Utility-scale compressed air storage costs roughly $23 per kilowatt-hour of capacity. A Powerwall, installed, lands somewhere around $1,000 per kilowatt-hour. That is a difference of more than 40 to 1. And the reason is simple. One of those systems stores energy as pressure in steel, and the other stores it in cobalt, nickel, and lithium that had to be mined, refined, shipped across an ocean, assembled into cells, and shipped again. So, you have a steel vessel that costs less than a car payment, holds pressure for decades, and requires no maintenance to do it. The question is what you put inside, and why pressure behaves so differently from chemistry. The principle is Boyle's law, written down in 1662, and it is one of the simplest relationships in physics. Squeeze a gas into half the space, and the pressure doubles. Squeeze it into a tenth, and the pressure goes up tenfold, provided the temperature stays constant. 360 years, and it has not moved. Now here is what that means for storage. When you compress air into a steel tank, you have done work on that air, and the pressure inside is that work, held. It does not decay while it sits. It does not have a cycle count. There is no chemical reaction happening inside that tank at all, which is the entire point, because chemical reactions are exactly what kill batteries. Compare that to what is happening inside a lithium cell right now, on somebody's garage wall. Every charge and discharge moves lithium ions back and forth through an electrolyte, and every one of those trips builds up a thin film on the electrode surface. That film traps ions permanently and takes them out of circulation. The battery is not breaking. It is working precisely as designed, and the design consumes itself. Which is why Tesla's own warranty on the Powerwall 3 guarantees 70% of original capacity after 10 years. Not as a worst case. As the promise, 70% is the number Tesla is comfortable putting in writing. Run that forward across the life of your solar panels, which are warranted for 25 to 30 years, and you are looking at 2 or 3 battery replacements underneath one set of panels. $30,000 to $45,000 in storage, spent to use electricity your own roof already made for free. And as of the start of 2026, the federal credit that used to cover 30% of residential storage no longer applies to systems placed in service. You are paying retail, every time. A steel tank full of air has none of that arithmetic attached to it, but a tank in a garage proves nothing on its own. What proves it is a plant in Germany that has been running since 1978. In Huntorf, in Lower Saxony, engineers built the world's first commercial-scale compressed air energy storage plant. It pumps air into 2 underground salt caverns and uses that stored air to help generate 290 megawatts of electricity. It went online in 1978. It is still running. That is close to 50 years of continuous commercial operation, on a storage medium that is, at bottom, squeezed air in a hole in the ground. 13 years later, A second plant went online in McIntosh, Alabama, built by the Alabama Electric Cooperative. It stores air in a salt cavern of about 19 million cubic feet and delivers 110 megawatts for up to 26 hours on a single charge. 26 hours. Set that against a home lithium battery sized for 4 hours of backup and you can see what a different category this is. The mining behind the alternative is worth a moment, because it is the part of the lithium story that never appears on the spec sheet. Most battery-grade lithium comes from brine operations in places like the Salar de Atacama in Chile, and research on that region estimates it takes roughly 500,000 liters of water, evaporated, to produce a single ton of lithium carbonate. That is water drawn out of one of the driest places on the planet. And at the other end of the life cycle, current estimates put the United States lithium-ion recycling rate at around 5%. The other 95% goes to landfill or sits in hazardous waste storage, waiting for an industry that has not been built yet. 2 plants in salt caverns, though, is a utility story, not a homeowner story. The homeowner story is much older, and it starts under a mountain. In 1857, French and Italian crews began drilling the Frejus rail tunnel through the Alps, and they did it with pneumatic drills fed by compressed air piped in from outside. Air was the only practical way to deliver mechanical power deep into solid rock without filling the tunnel with exhaust. That project took 13 years and cut roughly 8 miles through alpine granite, and it ran on the same physics sitting in a tank in your garage. 22 years later, an Austrian engineer named Victor Popp took the idea and wired an entire city with it. Starting in 1879, his company built a compressed air distribution network under the streets of Paris, running pipes beneath the roads to drive clocks, elevators, and industrial machinery across the city. That network operated continuously until 1994, 115 years. And it did not shut down because compressed air stopped working. It shut down because the industrial customers left, and maintaining century-old underground pipes stopped paying for itself. The technology never failed. The economics around it changed. So the principle is proven at tunnel scale, city scale, and utility scale, across 3 centuries. Which raises the obvious question about why there is no compressed air storage unit sitting on a shelf at your hardware store next to the generators. The barrier is not performance, it is paperwork. Every financial incentive and every certification pathway in the American home energy market was built around lithium chemistry. There is no UL listing for a residential compressed air storage product because no manufacturer has submitted one. There is no installer certification because there is no product to install. There is no permitting pathway in most municipalities because no inspector has ever been handed a plan for one. And without a certified product and a licensed installer, no tax professional will put it on a return and no appraiser will add it to your home's value. A homeowner who buys a wall battery gets a turnkey installation, a product listed in mortgage appraisal guidelines, and an insurance rider that covers it. A homeowner who builds a pressure vessel storage system in his own yard gets none of that. Nobody sat in a room and decided to block compressed air. The rules were written around the assumption that home energy storage means a chemical battery, and anything outside that assumption is invisible. In a market where certification decides what gets built, invisible works out about the same as prohibited. So nobody will sell you one. You can still build one, and the whole parts list comes to somewhere between $500 and $1,200. If you've enjoyed the video so far, we'd really appreciate it if you subscribe to the channel, because the number I'm about to give you is the one every other video on this topic leaves out. The vessel is your ASME propane tank. A new 120-gallon vertical tank runs $400 to $600 retail, and a used or decommissioned tank from a propane company clearing out older inventory sells for $50 to $120. For compression, you want an oil-free electric compressor rated for continuous duty at 150 pounds per square inch, which puts you at $200 to $400. Oil-free is not a preference. Any oil vapor entering that tank will sit inside it for years, coating the steel and fouling whatever you connect downstream. Between the compressor and the tank goes an inline moisture separator and a desiccant filter, $20 to $40. And this is the single component that determines whether your tank lasts 3 decades or 3 years. Dry air does nothing to steel. Damp air, cycled over years, corrodes it from the inside where you cannot see it. Get this right once, and the storage side of the system asks nothing of you again. If you want electricity back out, you need an air motor, $30 to $300 depending on size, coupled to a permanent magnet generator or a small automotive alternator, feeding a modest deep cycle buffer battery that costs $60 to $80. That buffer battery is not your storage. The tank is your storage. The battery smooths the output as tank pressure falls at the end of a discharge and gives your inverter a stable voltage to work against. Round-trip return on a home compressed air setup runs somewhere between 30 and 65%, against lithium's 90%, and that single number is why this technology wins somewhere completely different from where everyone tries to use it. Put a kilowatt-hour of solar into that tank and expect to get back roughly half of it, lost as heat during compression and lost again in the conversion back to rotation and then to current. Any video telling you a $150 tank will run your house off solar at no loss is selling you something. There is a second correction worth making, because it goes to the honesty of the whole story. Huntorf and McIntosh are genuinely remarkable plants, and they are not pure air systems. Both of them burn some natural gas during the discharge phase, using the stored compressed air to make that combustion far more productive than it would otherwise be. Anyone who tells you those plants run on nothing but air is skipping a step. What those plants do prove, decade after decade, is the part that actually matters to you. The storage medium itself never wears out. There is no cycle limit on a cavern. There is no calendar life on a steel tank. 50 years in, Huntorf's air still holds pressure exactly the way it did in 1978. So half your energy comes back, and the vessel lasts forever. Whether that is a good trade depends entirely on what you are trying to power. And here is where the real answer lives. Where compressed air genuinely wins, and where it has been winning for over a century, is powering things that run on air directly, with no conversion back to electricity at all. Off-grid workshops have done this for generations. Run steel pipe from the tank and you can drive table saws, drill presses, sanders, impact wrenches, and pneumatic water pumps without ever passing through a motor, a generator, or an inverter. No conversion losses, because there is no conversion. The air does the work as air. If you have a shop, a barn, a well pump, or a property without grid service, this is the version of the technology with 170 years of continuous industrial use behind it, going back to those drills under the Alps. Try to run your refrigerator off it, and you are fighting the round-trip number. Try to run your air tools off it, and the round-trip number never enters the conversation. Before you build anything, one safety rule that is not optional. Never use PVC or any plastic pipe for compressed air. PVC embrittles under pressure cycling and can shatter without warning, throwing fragments at speeds that will kill someone. Use black iron pipe, copper tubing, or aluminum rated for compressed air service. Install a pressure relief valve set to open 10% below the vessel's rated maximum. That valve costs under $15, and it is the most important component in the entire system. If you are designing anything above 200 pounds per square inch, have a licensed mechanical engineer size your piping and specify the relief valve. Stored pressure is real energy, and it does not care about your intentions. Maintenance after that is close to nothing. Drain condensation from the separator on a schedule. Check the relief valve once a year to be sure it has not seized, and look over your fittings for corrosion once or twice a season. No cell balancing. No thermal management. No firmware. The tank is the one component in your entire off-grid setup genuinely built to outlast everything else you own. The average American household uses around 10,500 kilowatt hours a year, close to 29 a day, according to federal energy data. No backyard tank is carrying that load, and pretending otherwise would be dishonest. But as a way to run a workshop off-grid, to drive a well pump without a generator, or to add a genuinely maintenance-free layer to a small solar setup, this is one of the few technologies where the core physics has been proven continuously at city scale, tunnel scale, and utility scale for over 150 years without a single battery cell involved. So here is my question for you. If you had a shed, a compressor, and one free weekend, would you build a pressure tank that returns half your energy but never wears out? Or would you write the check for a lithium battery that returns 90% and is guaranteed in writing to fade by year 10? Tell me which way you would go in the comments.